So in this video, we're going to be looking at nucleophilic addition reaction mechanisms for our carbonyl compounds. Before we do that though, we need to recap two things: our reactions of our alcohols to make these carbonyl compounds, and then the nucleophilic substitution reaction mechanism itself. Now when we look at haloalkanes, right, we know haloalkanes, they contain a polar bond because the chlorine atom in this case is going to be more electronegative. It's got a greater ability to attract electrons in a covalent bond compared to that of the carbon, and that's what makes our haloalkane is polar, that polar bond there. Now that partially positive carbon atom is actually very special because it can be attacked by nucleophiles such as those of hydroxide and cyanide as well, right? Two examples you would come across before. Now in this specific case, we're going to be doing an example of a mechanism of a reaction called alkali hydrolysis, where we would have our reagent in this case, which is going to be sodium hydroxide, and it needs to be warm and aqueous, and then we're going to have reflux as the apparatus itself. So in this particular example, I've got 1 chloro, 2 methyl, and then it's going to be propane. So in that case, the formula is going to be C, and then it's going to be 4H and then 9Cl, and that's going to be reacting with sodium hydroxide, and that's going to form, right, in a substitution reaction. We swap the chlorine for the hydroxide, we end up forming C4H9 and then OH, which is just going to be 2-methyl propan 1-ol, and then we also end up forming sodium chloride as well. Our actual atom economy in this case is not going to be 100%, right? It's going to be less than 100%. Why? Because it's a substitution reaction. You end up forming a byproduct, a waste product over here, and you don't only form one product itself, right? So in this case, right, how do we actually draw out our mechanism? Well, we end up with our hydroxide nucleophile carefully positioned so that we can get a curly arrow in there, and that's going to go from the lone pair, right, and it's going to go to the partially positive carbon atom itself. We're going to form a bond between the lone pair and the partially positive carbon atom itself, like that. Now if that's the case, we end up with heterolytic fission taking place. Our covalent bond breaks and both electrons go to the chlorine atom over here, and so we end up with our products as being our alcohol, which is going to look like this, and then we also end up with our chloride ion floating about that gets mopped up by the sodium ions itself as well. The sodium is going to be a spectator ion, right? Now you can see here we've got two arrows. They're both curly because they show the movement of a pair of electrons. They've got a full head on them as well because remember, in a pair you have two electrons, and you've got a substitution reaction here that involves a nucleophile, so we call it nucleophilic substitution. So moving on then, in that case, right, if I were to look at my carbonyl compounds, right, they're very special because they contain the carbon-oxygen double bond itself. And we consider aldehydes and ketones in A-level chemistry to be our carbonyl compounds. And if we were to look at that, right, there's two special things about this carbon-oxygen double bond. One of them is that oxygen is going to be more electronegative compared to the carbon. It's got a greater ability to attract electrons within the covalent bond itself. So we know that bond is polar, right, and so that's going to give us certain reactions that involve nucleophiles because we've got a partially positive carbon atom. But then because we've also got, right, the sideways overlap of our p orbitals on the carbon atom, which I'm going to draw over here. I've got one p orbital which has a dumbbell shape and another p orbital over here on the oxygen atom. These two orbitals are going to expand up until a point they overlap, and they overlap sideways, and so they create a pi bond above and below the plane, just like our alkenes themselves. Now I'm going to label this as well because I need to have labels on my diagram. I've got a p orbital over here, that's one p orbital, it's got dumbbell shape, and then I've also got here a sigma bond. And the second bond, right, which we're going to draw on there, is going to be our pi bond, which is going to look like this. One pi bond, which is going to be above and below. Now in this case, right, you can see I've got an arrow that says sideways overlap, and we've showed how our double bond is formed, but there's something missing on this diagram, and that is our partial charges. I need to have a partially negative charge on oxygen and partially positive charge on carbon itself as well, because a bond, remember, is polar. And so that's very important because we actually have a partially positive carbon atom that can be attacked by different nucleophiles, which we'll be looking at in this video, cyanide ions and hydrides itself as well. So moving on then, in that case, right, if we were to look at how we can form these carbonyl compounds, you need to think back to year 1 where we looked at the oxidation of our primary and secondary alcohols. In all cases, we're going to use sulfuric acid as our catalyst, and then potassium dichromate is going to be our oxidizing agent, which we represent with an O in square brackets. If we were to use distillation apparatus, right, we would separate our aldehyde out before we actually form a carboxylic acid, and so our primary alcohol would go ahead and form a aldehyde and one lot of water. But then if, let's say, I wanted to go all the way and do the complete oxidation rather than partial oxidation, I would use 2 lots of oxidizing agent, 2 equivalents, and I would use reflux apparatus. And what will happen is I will end up forming a carboxylic acid but still 1 molecule of water, right? And the reason why is because if you go from a primary alcohol to an aldehyde, you form a molecule of water, but in the second step, to go from an aldehyde to a carboxylic acid, which you can see in this bottom reaction we're doing, right, we still use reflux. We use 1 lot of oxidizing agent to go from an aldehyde to a carboxylic acid, but we don't form any water in that second step itself, and that's something that you have to be aware of. Now, if we were to look at ketones, how can we make ketones? Well, we take secondary alcohols in this case, and we form ketones through using, again, sulfuric acid, potassium dichromate, and reflux, 1 equivalent of oxidizing agent, so that's 1 lot of potassium dichromate, and we form our ketone using a secondary alcohol, and we also form water as well, right? You can see the position of the OH is going to be where we form a carbon-oxygen double bond itself. Now, in terms of tertiary alcohols, you need to remember that these cannot be oxidized, and so you can't end up with a carbon-oxygen double bond, which is going to also have 3 different carbon atoms attached to it. It just wouldn't work, right? Now, in chemistry, we know so far that having O in square brackets means that we've got an oxidizing agent, such as potassium dichromate, but the examiner could throw in some unfamiliar ones in there. And then now we need to know that the H in square brackets is going to be a reducing agent, and the one we have to remember is going to be sodium borohydride itself, where we actually have the important ion in there, the important nucleophile, which is going to be a hydride ion, which looks like this itself. Now, in terms of that then, right, that gives us a new mechanism that we can use, and that's going to be for the reduction of our aldehydes and ketones to form respectively primary and secondary alcohols itself, right? You can see I've got here a aldehyde on the left hand side, and if we look at an aldehyde, we know we make it from a primary alcohol. If we go in the reverse direction then, from an aldehyde to an alcohol, we will always form a primary alcohol as well, and that's something that you need to remember. Why is it a primary alcohol? Well, a carbon atom it's directly attached to, right, the carbon atom that's directly attached to the OH, the alcohol group, that only has 1 alkyl group itself. Yeah. Now, in terms of the balanced equation, right, you can see we've got 2 lots of reducing agent over here in the reactants, and the reagents that we actually use to make this reaction happen is sodium borohydride and water, and we just warm that mixture together with our aldehyde and ketone to actually form our primary or secondary alcohol itself. What about the mechanism? What's going to happen? Well, first of all, we know that we've got a partially positive charge on this carbon, partially negative charge on this oxygen itself, and we're going to have our first arrow going from our hydride ion going to form a bond to the carbon atom. So we end up with a curly arrow going towards this carbon atom over here. What's going to happen next? Well, that carbon can't have 5 bonds. 1 will break, and the weak one is going to be the carbon-oxygen double bond. The pi bond within that's going to break, and both the electrons are going to go to the oxygen atom. Now, our intermediate in this case is actually going to be an alkoxide intermediate, where I end up with, yes, my carbon chain. I've got 3 carbon atoms, and then I've got a bond to the oxygen, and then a lone pair on that oxygen atom as well. Turn it into an ion, right? Now, we've also got here floating about a molecule of water, which is going to look like this, and we're going to have some partial charges on there because water, we know it's polar, and so I've got my partial charges on there that look like this as well. We're going to protonate this oxygen over here, and so we're going to end up with a lone pair right here being donated. We're going to end up with a dative covalent bond where both electrons come from the same atom being formed between this oxygen and the hydrogen on the molecule of water itself. Now, once we've formed a bond to that hydrogen, our hydrogen-oxygen bond breaks, and so we end up with both of our electrons going onto this oxygen atom, and so we end up forming a OH minus ion. Now, our final product is just going to be our secondary alcohol, which is basically just our protonated alkoxide right now. Yeah, so in that case, there's my mechanism. You can see we've made OH minus here, but you don't actually show it in the overall equation. Again, it's an addition reaction, and the atom economy is going to be 100% as well, right? It's nucleophilic addition. That's what we call it, because it involves a nucleophile addition, because you're adding one molecule onto another. So moving on then, in that case, right, let's look at another example with a ketone. You can see over here that we've got a ketone, and we're going to reduce it to form a secondary alcohol in this case. Why is it secondary? Well, the carbon atom the alcohol is attached to is going to be attached to two alkyl groups itself, and again we use two lots of reducing agent. If you look at the overall reaction, I'm going from propan 2-1, I'm going to use two lots of reducing agent, and I'm going to have a propan 2-ol molecule being formed itself, the secondary alcohol. And again, remember, you need to have two lots of reducing reagent as well. Now if that's the case, again, the conditions and reagents are going to be the same. We pretty much just warm our ketone with sodium borohydride and water, and again we've got our partially positive carbon here, partially negative oxygen there. We end up with our first arrow going from the lone pair on the hydride to the carbon atom. The pi bond breaks, both electrons go to this oxygen atom. We form our alkoxide again over here, which is going to look like this, and I'm going to end up with an oxygen atom over here, and this time I'm going to put the lone pair on the top and then the negative charge over here. It doesn't really matter where it is, left, right or top, whichever you prefer really. And we're going to end up with hydrogen bonded to oxygen bonded to hydrogen. There's my molecule of water with the partial charges on there as well, and then we're going to end up with a dative covalent bond forming. So the lone pair, right, I'm going to draw an arrow going from that to the hydrogen, and then this bond breaks over here, and we end up with our final product, which is going to be our secondary alcohol itself, right? And then don't forget the OH minus that's also formed in there as well. Again, we don't put that in the overall equation, right? Now what about if you're dealing with some ugly looking ketones or aldehydes? Well, just remember, when it comes to your actual mechanism itself, you can actually draw, you know, your first arrow coming from the hydride or the cyanide, which we're going to look at next anyway. It can go from underneath like this, it can come from this corner like this, or from this corner like this. The actual angle of attack, right, these three ways that you can end up with your arrow coming from and going to, is actually called a Bogey-Dunitz angle, and that's what we should actually end up with and aim to get, going directly to the carbon atom in those angles itself. We've got that trigonal planar shape around the carbon atom that's bonded to the oxygen itself. So the next reaction that you need to know about, the next nucleophilic addition mechanism used in reaction, is the synthesis of hydroxynitriles, where you take something like an aldehyde or a ketone. In this case, we've got the aldehyde propanol, because we've got 1, 2, 3 carbon atoms over here. We react it with the reagents of H2SO4 and sodium cyanide, which gives us HCN in situ, right? So we end up making the HCN to react it with, and what we end up forming is an extended carbon chain over here, where we've added on a cyanide group and we've turned the carbon-oxygen double bond into an OH group itself. So in this case, right, our prefix ends up being 2-hydroxy, because no longer do we call it ol, and then we've got cyanide attached to the same carbon atom as well. So then it's going to be, now because it's a fourth carbon atom, it's going to be butane, and then we're going to end it in nitrile, because that's that functional group over here as well, right? So in this reaction, right, you end up with the same type of mechanism where you use cyanide as a nucleophile. So again, I've got partially negative, partially positive charges. My lone pair, I draw an arrow going from that to the carbon atom, and then we end up with heterolytic fission taking place. The covalent bond breaks, the pi bond breaks in this case, and both electrons go to the oxygen atom. So in terms of my intermediate then, what I should end up with is the following. I've got oxygen, again, I've got the lone pair on there, and this time I'm going to circle my charge so it makes it obvious to the examiner. But remember, you've also added a cyanide onto there as well, right? Now, what's going to happen next? Well, you've got some H plus floating about. You can use water. The examiner doesn't mind either in this case of the synthesis of hydroxynitriles, but I prefer the H plus. And you're going to protonate, right, this O group, right, this oxygen, and you're going to end up with OH itself. And so you end up forming your hydroxynitrile, which should actually look like this at the end. That's going to be 2-hydroxy butanitrile itself, and in this case there is no second product being formed if you use H plus. So moving on, right, feel free to pause the video and have a go at the following question. Once you're ready to move on, resume and we'll go over it. So yeah, if we were to look at this, we're told a carbonyl compound is reacting with NaBH4 and which compounds could be formed. So in this case, right, we're reducing an aldehyde or a ketone or something to form a primary, secondary alcohol. We need to draw these structures out to begin with. So I've got pentan 2-ol, so that's going to be 1, 2, 3, 4, 5. They're all going to be pent, to be honest. So in that case, I'm going to draw 5 carbon atoms on all of them. And if we look at the first one, right, it says pentan 2-ol, so the OH is here. The second one, we've got pentan 1-ol, and then the third one, pentan 2-ol. In terms of that methyl group, in the first two, it's going to be at the 2 position. And in the third one, it's going to be at the 3 position itself. Now, if I were to look at these, right, we need to think, okay, in which cases have we got aldehydes and ketones that form primary and secondary alcohols? Because we can actually only form a primary and secondary alcohol through the process of reduction itself. So I look at this first one, that's a tertiary alcohol. We've got 3 alkyl groups on there, and we can't actually oxidize that to form an aldehyde or a ketone, and we can't even go in the reverse process to form a tertiary alcohol. That reaction just doesn't happen. If we were to look at number 2, right, we've got a primary alcohol over here. So in that case, we must have had an aldehyde because we've only got 1 alkyl group on there that we've reduced to form this primary alcohol. So that's going to be fine, that could be formed. If we were to look at the next one, we've got a secondary alcohol, so we know that we must have had a ketone and we've reduced the ketone to form a secondary alcohol. So the correct answer in this case is going to be B and C, right? So moving on, let's try the next one. Feel free to pause the video and have a go at the following. So here we're asked to draw the structure of the carbonyl compound used to synthesize the following hydroxynitriles, right? So we know we have turned the carbon-oxygen double bond into a carbon bonded to OH, but then we've also connected a cyanide on there as well. So in that case, if I were to look at this, right, I'm going to chop the cyanide off because that's been added on, and then I'm going to turn this oxygen, right, carbon, turn it to a double bond and get rid of the hydrogen. So what I should have had is this molecule over here that looks like this. It's a ketone. So that's the original compound reacting with H2SO4 and sodium cyanide. Looking at the next one, right, I've got here benzene ring, which actually isn't involved in the reaction. The key bit is this bit over here. So again, we chop off the cyanide and then we add a double bond over here. So I've technically got for this one a benzene ring on this carbon atom, one coming down, one going up, and then we've got a double bond to the oxygen itself, and we've got an aldehyde here. Next one, we've got rid of this cyanide over here, turn that into a double bond. We've got cyclo, and then it's going to be pentanone. In this case, we've got a ketone here. Moving on, feel free to pause the video and have a go at the following. So in this case, right, looking at this, right, I'm going from an alcohol, right, to a hydroxynitrile itself. So in that case, right, we need to think about what we could have as an intermediate and how do we actually make hydroxynitriles. Well, we only know one way as of yet, and that is to use H2SO4. And we also know that we need something like sodium, and then it's going to be cyanide itself as well. Now, in order to actually form a hydroxynitrile itself, we must have had a carbon-oxygen double bond over here, bonded to our benzene ring, and in that case we must actually form benzaldehyde somehow. So in that case I should end up with benzene, right, the benzene ring, carbon oxygen double bond is going to be on there as well. There's benzaldehyde. How do I go from this alcohol here to an aldehyde group? Well, I know that we need some sulfuric acid catalyst. We need to oxidize it first, right, using our oxidizing agent of potassium dichromate, and then we also need in there a key condition which isn't reflux because that would make benzoic acid. It's actually going to be distillation itself.